Okay, welcome everybody. My name is William Blako, and I want to explain what is computational linguistics. Another name for it is natural language processing. It involves data science, lots of math, some programming, and artificial intelligence. And so I have slides prepared, but I am happy to answer any questions you might have throughout the presentation, so you can write those in the chat. Okay. So data science is an overall very broad science that I will show some examples of. And then what is linguistics, the theory of linguistics itself. And then we'll apply data science to textual data. And then go into some of the processes necessary for natural language processing. And one of them will be machine learning, which is another name for artificial intelligence. And then I will explain some applications specific to NLP. But first, data science in general. This is very general. You receive as input some signal, be it visual, audio, text, tweets, anything. And then you need to filter those data points and clean them so that you can have a data structure with those points in them. And you need to decide on the structure. So a lot of these steps are based on the decisions of the developer or the researcher. They're not always one size fits all. And then obviously you can do lots of statistical analysis because you're working with quantifiable data. And you will need to find some kind of encoding because you'll want to save the data on a hard drive. And the point of doing all this is to gain some valuable insights in the end. The example I thought of earlier today was, let's take a look at the convention this weekend. There are some speakers, there are tons of participants, and they could each be a data point, and then the task could be to predict which participant attends which talk. And we could use some attributes of the participants, for example, age, gender, country, the language they speak, their background, their interests, and some attributes of the talks, like the speaker, and similar attributes about the speaker, the title of the talk, the field, the subject. And then we could try to write a program that uses algorithms to predict which participant will attend which talk. And I'll go into some more details on what makes that possible. Let's look at some obvious examples of data science. So this is facial recognition. For us, it might be really easy to see that this is the same person, but for a computer, it's not simple at all because the face is in a slightly different position. So we don't easily know which pixels to compare in these two pictures. There's a cap instead of hair, and there's a beard and there's no beard. There's slightly different color to the skin. And one you see freckles and the others you don't. But if you train a computer program well enough, it will focus on the main attributes and not compare the pictures pixel by pixel, but say just, oh, there are two eyes and they're roughly in the same region, and the nose is about the same shape, and so on. And then ignore the irrelevant features. And still you'll only get a match of, say, 90%, because cap and hair is totally different. But you need to set a threshold and then say, okay, it's higher than 70%, so it's very likely the same person. Self-driving cars need to be able to detect objects. Postal service, for example, needs to be able to interpret handwriting. And here is an example of digits, what they might look like. And even though they vary every time slightly, the program needs to be able to tell that 5 is a 5, no matter if it deviates slightly every time. Speech is not as obvious as images, but we can turn sound waves into something visible like this spectrogram. And then you will see that, well, you can already tell some differences. For example, I should say this is not the frequency pattern that you're used to from a sound wave. This is the Fourier transform of that, so that on the y-axis are the different frequencies, and on the x-axis is the time, or the sounds that are being made when a female speaker says children like strawberries. And here you have ch, and here s, and here is z. And so these are at the top, and these vowels, for example, I, I, are at the bottom. And I'm not an expert on this stuff. I concentrated on text processing in my jobs, but you can see this is already one obvious feature that you can use to distinguish different types of sounds. And then there are others, of course, like probably these patterns inside of this field will tell you something about the path that the sound is taking. Like I goes from A to I, right? Goes I. Anyway, that's something that you can then apply image algorithms to, because we turned sound into an image. When it comes to text, there are some things you can do with, well, there are lots of things you can do with text in order to quantify it. And that's what we want. We want to turn anything into a vector and then train artificial intelligence with those input vectors to determine what makes them choose, or what attaches this input to this output. What's the underlying function? And we can use some of the characteristics of words in natural language. And here's one that you'll find in every language, even the ones that have already died in the meantime. For example, if you collect millions of documents or web pages, for example, and then just count how often each word appears, then you will find this pattern in all languages. So the most common word will be the, and then the next will be of, and then a, and so forth. So words that have very little content, and then the less common words as you go along will have more meaning to them, like people or now, I would say, are more content words, whereas these other words, like this and in and with, are function words. They make sure that the sentence is grammatical, but the content words convey the meaning. And here are similar distributions from other languages. The one on the bottom left is Hebrew. I'm not sure what the others are, but you will see the same Zipfian distribution for words, and you will find, I can't confirm this personally, but you will find that function words, with little meaning, but they're rather there for the well-formedness of the sentence, will be more common than the content words. But this is only one attribute of natural languages. What can we do with such occurrence counts in large collections of texts? Well, we can do one thing, that is predict their word similarity. So when a word appears in the context of content words like, let's say, jungle, hunt, food, danger, and another word appears in the context of those same content words in its own sentences somewhere else in the collection, and those context words are there with the same frequency along with the target word, then those two target words are likely to have a very similar meaning. So I was talking about the context of jungle and danger. because this is from a data set where people should judge between 1 and 10 how similar two words are. And tiger is 8 out of 10, similar to jaguar, and the same with feline, but it's not as similar with mammal or organism or fauna because, well, even though there is some commonality there, those words on the right become less and less specific to tiger. So a jaguar has more in common with tiger than an organism in general, and therefore it got a lower score. And then we test. So these are from human judgments. This is a data set with annotations from humans, and then we try to find an algorithm that will take these input words and predict the same output similarities between them. And if we do get a good correlation between the two, then we have found an algorithm that is good at understanding some aspects of word meanings. And then we can use that for further applications, which I'll show some examples of. Okay, let's quickly go over what is linguistics. It is not learning a foreign language, and computational linguistics is not principally about learning or studying computer languages. We are processing natural language using programming languages, but we're not analyzing programming languages. So how does human language work? Well, human communication, let's start there, because language goes even deeper. The speaker has a thought in his head, turns it into sounds, into a sequence of sounds, conveys them to the listener through the air by using his diaphragm and tongue and lips in order to create vibrations in the air. Those air waves reach the ear of the listener. Then that signal gets interpreted in many complex ways and goes into their brain. And then they hopefully have the thought that the speaker had originally. It never happens that perfectly, but and it's even more difficult for a computer to simulate these processes, but let's try anyway. So in linguistics, phonetics is the study of biology, what creates those sounds. And these sounds are then distinguished by different symbols. It's a huge mix of Latin and Greek symbols. And when you throw all the sounds from all the languages in the world together, you get this huge inventory called the International Phonetic Alphabet. And you can then dissect them by giving them attributes. And then you only need to differentiate between those attributes. For example, here on the x-axis is where the sound is articulated. So does it use teeth, for example, dental? Does it use lips? And on the y-axis is what type of articulation. Plosive means like the air is blocked and then suddenly released. Fricative means the air is let out slowly, but with some resistance, like or zzz. And there are some others that we don't need to get into. Nasal is when the mouth is closed. Well, not the whole mouth doesn't have to be closed like with n. With n, you're blocking the airflow from behind, but the air still goes through your nose, which you can confirm by going with your hand at your nose, and you'll see air coming out. Anyway, those are the consonants, and these are the vowels. So think of the mouth again, the exit being to the left. Front is on the left. And then if you really analyze it, sounds like E and E and E and I are towards the front, and sounds like oo and o and aw are towards the back. So these are ways that scientists have categorized the different sounds. And it's also useful for computers then to process them, rather than having to deal with these frequencies or these spectrograms. Just using the most necessary data to distinguish them is helpful when applying computer programming. Yeah. this is not so relevant. I already covered this, but just to show what it then looks like when people transcribe sounds into phones or sound waves into sound script, I could call it. So even though this is, we write this the same, TH, there are different sounds, right? This is thick, not vocalized, and this is though vocalized, right? Here you use your vocal cords and here you don't. And therefore they have different symbols and a different collection of attributes. Phonology goes into the rules that apply to sounds in context of other sounds. So here, the focus or the emphasis is on the first syllable, right? Able, super, photograph. The first syllable gets the emphasis. Here, even though the word is totally related to the one on the left, the first syllable is no longer the emphasized one, and therefore A becomes A, U becomes and O becomes O. So you could formalize this rule that the vowel gets neutralized when it is not in a stressed position, as on the left. Morphology is when sounds are put together. Well, we'll look at the next bigger unit, which is a morpheme. So the word morphology has 4 morphemes. Morph is Greek for form. Log is Greek for speech or word. Logy is Greek for the study of, like biology or psychology. And this just the O just connects the two to, I don't know, it's probably easier to speak, to express the word that way. And then these partial words each have their meaning and are put together to make the meaning of the whole word. Kind of like the meaning of words are combined to make the meaning of a sentence. And in some languages, this distinction isn't really there. Maybe Chinese, where it's not even clear where one word begins and ends. They don't have spaces, for example, which is an indicator of that. And there, is this a part word? Is this just more like a suffix, or the core of the word, or is it just a part of a sentence? That it's more intertwined than in English, for example. Syntax is probably the closest to what you consider grammar. And this is where the structure of a sentence is in the form of a tree. So the sentence is, a woman was injured by a falling tree in the neighborhood, in the Gresham neighborhood. At the root of the tree, linguists always say the root is at the top and the leaves are at the bottom. At the root of the tree is the verb of the whole sentence. And then it's in its passive voice, right? So the subject is the person being injured. If it were in its active voice, you would have a subject doing the injuring and an object being injured. But because it's passive, a woman is being injured, but is in the subject position of the sentence, right? That's what passive is. And then there is a prepositional phrase with the preposition by, which gives you the thing doing the injuring. So that's a tree. And then here are the things modifying the tree. It's a tree, it's a falling tree, it's a tree in the Gresham neighborhood, right? And so the higher up a word is in the tree, the more of a fundamental role it plays in the meaning of the sentence, and the lower it is, the more of a modifying role the word plays. These trees can be really useful when distinguishing different meanings of the same sentence, because as you know, ambiguity is everywhere in language. Not just a word having 2 different meanings, but in this case, a sentence having 2 different meanings. So the boy saw the man with the telescope can either mean that the telescope is a tool that the boy is using to see the man, or that the man is holding the telescope and the boy sees him, right? And this is made explicit in the trees. So here is with the telescope. I hope you don't get confused between the words on the rows and the words between the rows. So, here with the telescope is a prepositional phrase modifying the man, and here with the telescope is a prepositional phrase modifying the seeing, how the boy sees the man. And then linguists try to take all this information. They rely heavily on these syntax trees to come up with logical formulas to express what is going on. So just a tiny sentence, "A woman smokes," already looks like a weird formula, if it's new to you anyway. This is predicate logic, also called first-order logic, and it expresses that there is, this is the existential quantifier, there exists an X from all the entities in the world, be it people, rocks, tables, animals, anything. There is an entity X such that X is a woman and X smokes. This is the logical way of writing "a woman smokes." Then use the universal quantifier. All X, for all entities X, if X is a woman, then X smokes. All right? So this doesn't tell you anything about whether a tiger smokes or not. You just need to cover all of the entities that are women and check for each of them whether they smoke or not to see whether the sentence is true or not. If you have a soliloquy like this, like Aristotle is known for, you can write it down with logical formulas. Every man has a head. Aristotle is a man, therefore Aristotle has a head, right? And the computer is able to take this formula expression of the natural English sentences, take these two premises together and reason that the consequence is that Aristotle has a head. So here X is a variable, and for every X, if X is a man, then X has a head. A is a constant, and this expresses that A is in the set of all men. And this is the consequence of taking the two premises together. A is in the set of all entities that have a head. Pragmatics is using language in context, in everyday situations. You might not notice this explicitly, but we do it all the time. We don't say literally what we mean. And this is often a contention that men and women have, because apparently men are more explicit and literal with what they say. But anyway, I don't want to get into that argument. It's just maybe you've been in that argument before. So when Anne says, "I have 2 children," Bob might think, well, she could have 3 children, and the sentence would still be true. But if she had 3 children, I think she would say she has 3 children. So she only says as much as necessary, and then your internal reasoning should be enough to figure out what she means literally. And this is normal. This is not just a female thing. This is, everyone uses it, but in slightly different ways. Or if let's let Bob say something that is not literally. If Anne says, "I'm out of gas," and Bob says, "There's a gas station around the corner," he wouldn't say that if the gas station were closed, right? Anne can safely assume that the gas station is open, even though Bob didn't say that explicitly. So this is pragmatics. This is going beyond this is reading between the lines, you could say. And it can be formalized so that, again, computers can work with it. So let's focus on textual data, no longer sound waves or images, because that's just what I've worked on throughout my career. We need tons and tons of texts. So what's the cheapest way to do it? Web scraping is one way to call it. You have a program that scours the internet, that jumps from page to page using links or search engines, and then downloads the HTML file that you don't see. You just see the nice, colorful, rendered version of it in the browser. But you take the HTML file, here's a tiny file, then you figure out what is the structure in that file, and you only extract the pure text, remove all the tags that the browser needs to know how to represent, how to show that file. Then you need to do a lot of cleaning of the data, usually, because anyone can tweet anything. For example, tweets are some of the noisiest data out there when you're working with text. There are tons of, well, lots of different ways of writing single and double quotes, for example, and you might want to map them all onto just one version of single or double quotes if you don't care about the subtle differences. But that depends on your application, of course. And then there are some other HTML codes that are commonly used to distinguish tags from pure text, because that's also useful information. But then you have, as an output, one document per HTML file containing several paragraphs. So what can we do with that once we have this clean collection of text? Usually we need millions of web pages containing billions of words. Well, now we need to clean up the content of each sentence. So if this is a sentence that we got from this collection of text, also called corpus, the strong-willed horse couldn't have escaped, then it's really simple for us to tell what are the words and where do they begin and end. But for a computer, it's not so simple. Even though English has spaces between the words, it doesn't always. For example, escaped dot. They're two different tokens, right? So token is more general than word. It can also be punctuation marks. But we don't need that as humans. We just know those are two different tokens. But you need to write a program that figures that out. Same with strong-willed. You could look at it as one word, but it's useful for many applications to separate those. And then it's up to you whether you want to include the hyphen as a token or not as well. And couldn't, in other words ending in nt, like haven't, are usually separated because nt, it has pretty much the same meaning every time it appears. It negates the verb in front of it. And when you remove it, you have a nice formed word, verb. So that's something typically done in English, which is useful. Next, it's useful to assign each token part of speech, whether it's a noun, verb, punctuation, and so on. Then if you want to reduce the amount of different words that you're looking at, which can be very useful, you can lemmatized every word. So that means bring it into its base form. So you ignore things like plural or singular. So every plural noun becomes a singular noun. With verbs, every tense is ignored. So could becomes can, willed becomes will, escaped becomes escape. And then you have a slightly smaller inventory of different tokens that you need to cover with your algorithm. Chunking is a shallow way of analyzing sentences and dividing them into noun phrases and verb phrases. But this is only a pre-step to parsing. So again, creating syntax trees. And there are lots of different ways of doing that. This is the sentence from earlier. The strong-willed horse couldn't have escaped. So again, escaped is the main verb, the main action we're talking about, and it's about a horse. And here's the auxiliary verb, and it's negated. And the punctuation isn't always useful because it's not pure linguistics. We don't say period at the end of a sentence. We raise the pitch of our voice at the end of a question. So that could still be useful, rather than knowing that this is just an indication of something. It's asking something. So I guess punctuation can be useful or not depending on your application. And again, we use such syntax trees to come up with, well, we can use it in many different ways. We use all this stuff, like the tokens, the parts of speech, the lemmas, the chunking, and the syntax trees can be used for many different applications, like trying to figure out the meaning of the sentence. And how to get from those data points to a logical formula is not simple at all. And logical formulas are, by the way, not the only way of expressing the meaning of words and sentences. We might get into that. Machine learning can be complicated, but I want to give just a really quick overview of the things that it almost always entails. So again, we start with at the point where we have a clean structured data set. And let's say the data set is a collection of sentences. So each data point is a sentence. And then we try to quantify that sentence and create a vector from it, because the algorithms that we'll work with use vectors as an input. And by vectors, I really mean that collection of numbers. So let's look at some obvious quantifications. In a sentence, how many words does it have? For each word in that sentence, how many characters does it have? And then you can have some yes/no features, like does it contain direct speech? Does it contain the word not or nt? And this one is not yes or no. This one is, what is the final punctuation? Dot, question mark, or exclamation mark? And here you can't just give them values like 0, 1, or 2, because there's no like arithmetic relationship between question mark and periods, but there is between 0 and 1 and 1 and 2. So instead of doing that, you, what's it called? You binarize this feature. You say one feature is final punctuation is dot, yes or no. Final punctuation is question mark, yes or no. Final punctuation is exclamation mark, yes or no. And for no, you put a 0 in that dimension of the vector. And for yes, you put a 1 in that dimension. And that works. That is allowed mathematically. So once you've done this for every sentence, you have a feature vector for every sentence, a totally numerical representation of that sentence, which obviously is not enough to convey to, you cannot reconstruct the entire sentence, with all its richness and intention from just this vector. But that's not what we want. We want a vector with only the data from the sentence necessary for the application that we have. So applications like understanding what are people writing. Okay, then you divide the data sets, the data points, into 3 parts: training model, training set, which is a large portion, and then 2 smaller portions for developing the algorithm, and then testing the algorithm to see how close does it come to human annotations. So I gave you earlier an example of word similarities, which was just a small excerpt of a data set where humans gave a pair of words a score between 1 and 10, depending on how similar they judged those words. And you let 20 people or so do the same task, so that you get an average value for each data point. And then my algorithm will try to simulate what humans did. And if it comes close, if the predicted values between 1 and 10 that the algorithm gives me are highly correlated with the values that humans give me, then I'm onto something. Then I found an algorithm that is good at doing this particular task that humans do. Obviously, it won't be able to do everything else that humans do. But in science, in research, you need to limit your search space, you could say, your variability, because computers and humans can only handle so much exploration or diversity with each experiment. So there are algorithms for each task in particular. The metrics used to decide whether an algorithm is good or not is often precision, recall, F1 score, and accuracy. And I don't have the time to go into how those are mathematically computed, but I just wanted you to see those words because they'll pop up over and over if you decide to work on anything in this area. But like I said, you try to achieve a close match between what your algorithm predicts and what humans actually did. This is a graphical representation of those 4 metrics, 4 different parameters. They're given as a percentage between 0 and 100. Okay. So I keep saying algorithm, but in machine learning, scientists actually say models, because what you're doing is modeling human behavior, right? And so if we think of different ways that humans learn, we can mimic those with algorithms. So what a algorithm does, or what a model does, is learn to find the connection between the inputs and the outputs so that it predicts the same as what humans do. And unsupervised learning means that whenever, let's see, there is no annotation to, okay, let's say you don't, let's say you have a data set where each data point is a sentence, and then humans, no, we could stay with word similarity, actually. So we had the human annotation, which is the supervision. That is the supervised signal. The label, the annotation 1 to 10 is what you're using to learn from. You know, if your model predicted something totally different than human annotation, then you need to change the model. And that is part of learning, you know, trial and error, you could say, and then keep adapting and improving. So you have that output signal to go by. If you don't have it, then you're doing unsupervised learning, which, you know, usually isn't as powerful, but it still has its perks. For example, I can represent the meaning of words or sentences with these feature vectors, and then I could just check which of the vectors are closer to each other than others in the vector space. And it turns out that if you have if you did good, if you selected a good set of features, then words that have similar meaning will be closer in the vector space than words that have very different meanings. And we call this observation clustering, because you will find a cluster of words that have similar meaning in the vector space, and you know you find those neighborhoods of vectors by computing the distance, the Euclidean distance, usually between pairs of vectors. And reinforcement learning is when an artificial intelligence is in a space of many possibilities and just explores, just tries out things, and then it has a reward function. I'll give you an example. Some years ago, a research lab in Google created an AI that beat the world champion at Go. You know, the Chinese game Go is so much more complex than chess. A computer beat the world chess master in, I don't know, the 80s or so. But for Go, it took a lot longer, you know, until maybe, I don't know, 8 years ago. And their algorithm is called AlphaGo, if you want to look it up. And the space is so huge because I don't know if you've seen it, the board for Go has, I don't know, 100 positions that you can put these little white and black pieces on. And just the combination of all the possible ways that the black and white pieces can be on the board is so huge that it's impossible for the algorithm to just go through all of them. Instead, it keeps trying new strategies and seeing how well it does. And so the reward function will be, do I win the game or not? And it, as training data, it used games from, you know, the records of games from world masters, tons of those, but that wasn't enough. After that, Google used 2 copies of the same model and let them play against each other. And so it could learn from itself. And that was, I think that's called self-supervision. Anyway, there are lots of different strategies. And lots of different models for machine learning. I will try to explain one of the most common and popular ones, called neural networks. It is inspired by brain neurology. brain biology. Human brains have billions or trillions of these neurons. You see 3 here. In the middle, it has the nucleus or soma. And then as inputs, it has dendrites, where you get these chemical signals coming in. And when enough of the signals have accumulated in the nucleus, the cell will fire. So it will send its own chemical signal along the axon and pass it on to all the other cells that are attached to its, I don't know what these are called, but again, other cells, dendrites, get this signal as its input. And so you have this communication, and you might think that, oh, this is super simple, basic. How is it supposed to achieve anything? Well, consider that a computer is only based on 0 and 1. So it's also a simple signal, but you can encode anything with just the differentiation between 0 and 1. If you have enough bits here, you need enough neurons to model the phenomenon, in our case, the linguistic phenomenon that you're trying to simulate. But of course, the brain's activity is super complex and cannot fully be modeled by a computer. So we need to strongly simplify it in order to make it practical. And maybe you'll recognize this. So we're going from left to right. In the middle is the cell nucleus. And here we accumulate the signals from different sources, via different dendrites. This input signals are x1, x2, down to xn, and they're each weighted. They're each multiplied by a weight w1, w2, and so on. The more important an input signal is, the higher its weight should be, because the weights times the input signals are just multiplied and summed up. So at this point you no longer know what's inputs contributed, what weight. And then when I don't know if I mentioned this, but this firing of the axon happens once a certain threshold of input signal is reached. So here we just say when these inputs times their weights summed up surpasses a certain threshold, we send out a 1, otherwise send out a 0. Okay, that's how that is simulated mechanically. And how is this useful? Well, let's say the output is whether a word has the same meaning as another word. So that would be a 0 or a 1. And let's say for a certain word pair, my neural algorithm, my neural model, predicted a totally wrong output, a totally wrong similarity value. It's very different than the human one. Then that information gets passed back to where the weights are, so that they're adjusted. If the algorithm says, well, actually, the signal from x1, you should have paid more attention to it and paid less attention to x2. So increase w1 and decrease w2, and then try again. This gets repeated a lot over and over. So you have feed forward, which is sending the information forward, and then you compare the output with the target, with the human, the perfect value, and then you send back the discrepancy and adjust the weights accordingly. That's basically how that works. But this was only one cell. Obviously, like I said, we need tons of cells to be able to encode what's going on in human word similarity judgments. And so here we have 5 inputs, and they don't go straight to the output. They first go to an intermediary layer of neurons. So each input, so this isn't really a neuron, it's just one input signal, but here you have a neuron. Input 1 gets passed on and on its way multiplied by the weights W, passed on to each of these hidden neurons. They're called hidden because we're trying to figure out what is the hidden function that takes inputs and gives me outputs, you know, the hidden function inside the human that describes its behavior. You might be able to tell by now that computer scientists think that humans are machines, just very complex machines. Anyway, the output, the weighted input gets passed on to every hidden neuron, and this happens for every input value. And then this is reiterated. You again multiply each hidden value by the weights on these arrows, they're not indicated, and then sum up and then see, do I surpass the threshold or not? And there are also thresholds in the hidden neurons. And then the more neurons you have and the more layers you stack up, the more powerful the network can be in describing or learning some behavior or phenomenon. And when you have more than one layer, you're talking about deep neural networks. Maybe you've come across the term deep fakes. That comes from deep learning or deep neural networks, because neural networks like these have been used, you know, to create pictures and voices and video of people that look totally realistic but are fake. Maybe you've seen like voices of George Bush saying something that he would never say, because someone managed to learn all his mimicry with a neural net and then reproduce, well, yeah, first of all, reproduce what he actually said, and then learning the underlying attributes needed, you know, only the necessary data and ignoring all the irrelevant data, and then making him say whatever they want. That is actually possible. I don't know how much work and time it takes, but it's possible now. So I wonder how much videos will be trusted in court, for example, in the future. So the abstract idea behind having several layers is that each layer learns and is built on top of the insights from the previous layer with facial recognition, for example. If you think of the two face photos in the beginning, first of all, you're working with pixels, right? Each pixel has a color. That's all you have. But you don't want the exact position and the exact color of each pixel to be what you're working with. You want to be a bit more flexible. So you might say, I only want to figure out where are the contours, the edges of the different parts. You know, where does a light color and a dark color come together, and that is how I detect edges. That could be your first layer. And then how do edges work together to make objects, like here's an eye and here's a nose. Third layer could be, how do these facial features make a face? And the fourth layer could be, what is the orientation of this face? Like will the algorithm detect that this is the same as this, even though it's a totally different picture for the computer? But if the algorithm is smart enough, it can tell that it's the same face, just slightly rotated. But let's return to text applications. Okay, language modeling is what researchers call predicting the next word. Today, the weather is nice, and a lot of different words could appear at this point. For example, outside, or in China, or in my mind. You know, it could be even more abstract than that. Or just for 1 hour. And these different responses, or, you know, auto completions of the input have different probabilities, and the algorithm will then try to, again, learn and do the same thing that a human would do, so that you're able to, I don't know. Oh, one application that I want to try someday is, I heard that someone could figure out that the Book of Mormon is written by lots of different authors. And I think they use something similar to this, you know, but this author would have said this in the same situation, like at this point in the text, whereas this other author said this, because they have these different preferences, or it's just how they speak or how they write. And so this method can find subtle differences. If you apply language modeling to characters, so just to see in English, what is the most likely letter to come after W-E-R? Well, it's E, right? Or I don't know if there are others, but in another language, it might be different. And so you can apply the same logic to just the single characters in the sequence of characters in a text and find out with high level of confidence what language a certain text is written in. So things like that I think are really useful. Then any of the tasks that I mentioned earlier, like tagging words with parts of speech or disambiguating the meaning of a word or the structure of a sentence, can be done with neural nets or other kinds of algorithms. Topic labeling, let's say, so at one of my jobs, a typical need from a customer was, we have millions of documents in our company, and it's just growing and growing, and we no longer have the structure and the overview that we used to when we were a small company. So we would like to create a database of all our documents, a so-called knowledge base, so that we can query it, kind of like a search engine queries the internet, and so that we don't need to go through all this data every time we're looking for something in particular. And therefore, can you automatically annotate all our data so that for each document, we know what the topic is. We don't want to go through it document by document and do it by hand. That would be the safer way of having more precise data, but it's not worth the effort. It takes time and money. And so can you come up with an algorithm that will classify the topic of each document? And you can do this for lots of different attributes and annotations of texts. And once you have indexed the documents in this way, you can find what you're looking for a lot more precisely and a lot quicker, because it's now in a data structure that has a really good structure. But usually you have to know the exact need and data of the collection of the company in order to know what kind of structure and attributes you're looking for. Arrow can mean that time is a noun and that it flies, or you could say give flies, so one fly, two flies, give flies the timing that an arrow has. And obviously the second one is not plausible and not usual for humans to say, but from a plain formal perspective, so for a computer, it's totally fine to say this, because it doesn't care whether an arrow can be timed like a fly. It doesn't have that knowledge, but we do. So we can tell right away that the first sequence of part of speech tags is the more natural one, but a computer first has to learn from lots of data, which is more likely. Parsing is what I mentioned earlier, assigning that tree structure to a sentence. Named entity recognition is something you want to find all the documents that talk about some interaction between France and China at a United Nations meeting. And so you want to annotate, you want to find automatically all the locations, all the organizations, and all the persons, and whatever other entity type you're looking for in documents, so that you can more easily and quickly query them for that. Semantic parsing is assigning every part, well, every relevant part of a sentence that's doing the offering. Recipient is the one receiving the offer. Reimbursement is the theme or the thing that gets offered. And last March is the time when it was offered. Another way to look at the different things going on around the verb offer. And yeah, question answering I get into later. Paraphrase detection is good for, let's see. Oh, I haven't checked in a while whether anyone has written any comments. If you, yeah, I think it's not possible when I share my screen. Any questions? I don't know what's happening. And maybe I should wrap up here. You want to know whether two sentences have the same meaning, and sometimes it's simple because you can just look at the words. Lots is like many. Wear shoes is like have shoes on, and black is like dark. So you can reduce the paraphrase detection of two sentences to the paraphrase detection of the words in those sentences. But sometimes it's not so simple. Like Paul is a factory worker, and Paul works in a factory. They might contain many of the same words, but they have a very different structure. Like one is about what Paul is, and one is about what Paul does. And for a computer, that could be sentences have the same meaning as the top one. Inference is trying to figure out when one sentence implies the other or entails the other. And this can be useful when proposes another sentence and you want to know whether that follows from what you know to be true. So I can't think of a very concrete example now, but you want to do some reasoning. You want to figure out whether, oh, let's say, for example, fake news. You want to say, these news sources are authoritative, I trust them. These news sources, I don't know about them, I'm suspicious. I would like to figure out if they contradict the first group or not. And so I will see whether they're compatible logically. That's at least one way to see how authentic one news source is. And then information extraction is basically, I'm sure, download the slides at this address or look me up on LinkedIn. Maybe take a screenshot if you're interested in that.